recording. So just like when we moved from forces to energy, we're doing the same thing now, moving from our electric fields and our Coulomb's law. Coulomb's law is our force. Electric fields give us another way to look at how things are going to move. But now we're going to start trying to get away from having to worry so much about that vector notation. And then we're also getting to a point where we can actually measure something, and we're going to start building devices, which is really great because we're going to define our first electrical device. So again, you do have this PowerPoint, it's PDF, and you have a study guide that goes with this. So just like what we did with energy, or just like what we did with forces, we defined work. And work, of course, has my favorite definition. Energy is the ability to do work. And we showed that work and energy were conserved. And we talked about the fact that we always have total conservation of energy. And we can look at potential energy and we can look at kinetic energy. And one of the great ways to look at that is our slide, where we're going to go up the slide. That's the amount of work done. That's the total energy we put into the system. And then as we're moving down the slide, we're changing from potential energy to kinetic energy. We kind of reviewed this when we were dealing with simple harmonic motion. And we started talking about some other energies. We have our Hooke's law, which is our spring energy. But now we're going to be talking about electrical energy. There's lots of different types of energies. And one of the things that we deal with those energies is we talk about things that are conservative and things that are non-conservative. So if I had friction, for example, I would lose heat to the surroundings. I still have conservation of energy, but I don't have that energy that allows me to do work because it's gone into the environment. Now, we don't have so much of that in terms of our electrical energy, but you guys do see that. If your cell phone gets warm, what happens to your battery? Your battery drops off and your battery life just drops off really, really quick. Other things that you'll see about electrical potential is if you have an app that somebody hasn't programmed very well, you'll notice that some of your apps are energy hogs in your cell phone, and they will drain the life of your battery. So we're looking at that electrical potential, and we can actually think of batteries as charge storage. And that's what we're going to start seeing with capacitors, is that capacitors are charge storers. And we get batteries from capacitors. So let's look at our system here. And our system is we're going to have a line of charge that's positive. We're going to have a line of charge that's negative. And by having that line of charge, and when you play with your laboratory, I encourage you to do these two lines of charge, because what you're going to see is you're going to be able to set up a uniform electric field between those two plates. And that two plates there is going to give us a capacitor. That's going to be an actual device. But the one thing that we know is like charges repel. So in order to have this positive charge here, I'm going to have to do work to move that positive charge to this one, because as soon as it gets so close to this, it's going to want to shoot off towards my negative pole. So for going from our traditional idea of work, we can change our force equation here to that force that we defined in our last chapter, that's our charge times our electric field divided by the distance between our two plates, or the distance that we move back and forth. And we can define that as our change in potential energy divided by our charge. And this defines our idea of electrical potential. So we have that. So the electrical potential of a point charge is going to be a little different than what we saw from our electric fields. Potential is going to have a 1 over R behavior. So if we go back here and look at this, if I go back and I look at this part here, I've got that distance that I'm traveling, and that's where that goes away when we're dealing with our electrical potential. Now, you also notice I no longer have that vector notation. So just like adding up my energies, I don't have to worry about if it's positive or negative. And several of you have emailed me and said, I think I've got it and I understand Coulomb's law, but when I plug it in, I've got it backwards or I've got it not quite right. So one of the things you really have to be careful about is reading the problem and saying it's asking you to calculate the force. Make sure you're calculating the force on the right charge, because if I calculate the force on the other charge, my direction of my force is going to be different because I'm looking at it from a different perspective. So you really got to pay attention to that. But now when I come over to electric potential, I don't have to worry about that so much, which is really nice. So just as our electric field drops as 1 over R squared, my electric potential drops as 1 over R. So we actually see this. And what's really cool, we can measure this. We can measure our electrical potential. We can measure volts. So if you have a multimeter in your house where you can check to see if you have a dead battery, you are actually measuring electrical potential. It's, you know, it's hard to measure electric field because electric field's in volts per meter, but my electrical potential is actually in volts, and we can actually measure that, which is really, really great. Now, when we were doing our charges, so I have my 2 charges, and then we're looking at the electric field at some point here, and I had to add the force from this charge, and I had to add the force from this charge to get the resultant force. We use something that we call the superposition principle. We're using the same thing here with my electrical potential, but now I don't have to worry about that vector notation. So if the potential from there to there is 3, and the potential from there to there is 5, I can just add them together. 3 plus 5 is 8. And it's going to make it a lot easier to work some of these problems. So the electric potential at some point P, due to several charges, is just going to be the algebraic sum of those various potentials. But I do have to worry about the positives and negatives. If I have a negative charge, I have to carry that negative with me. If I have a positive charge, I have to carry that positive with me. So that's something that we do have to worry about. So just like what we did here, my potential energy is going to be adding at some point here, and we'll just add them together and we can look at that work. So again, tomorrow we'll work some extra problems. You actually have some example problems in Blackboard, but that will get us, and we'll work those problems a little bit tomorrow and get us going there. But conductors in equilibrium, if I have a conductor, all the charge is going to reside on the surface. All our acting working charges resides on the surface, and my electric field inside my conductor is 0. So when you're actually drawing your electric fields in that lab, I encourage you to get a closed space so that you can actually see that. Additionally, the field is going to be perpendicular to the surface. And that's when you're going to start to see that the charge is going to get, your charge density, for a lack of better anything else, is going to get really big at sharp points or sharp curves. So the potential is constant everywhere on the surface of the conductor. The potential everywhere inside is equal to the value of the surface. So you can have those conductors in equilibrium. Good news is We don't have to worry about that so much. We play with it. It explains why lightning rods work. It explains why if I put my finger towards the light bar or towards the doorknob, I'm going to get the zot. It explains why that's where you're going to get that charge, that it's going to come through, and that's where the spark is going to be. But for what we do, it's not as a big of an issue. It just helps us explain that concept that we see. We can also define things as terms of electron volts. For those of you who are doing radiology, dealing with x-rays, dealing with a lot of different things, we sometimes work with electron volts versus joules because it's handier to work with out there in the real world. Because it's a lot easier to deal with 1 electron volt than 1.6 times 10 to the minus 19 joules. So we get a better picture of what is happening if I want to use that. So sometimes we'll do things in electron volts, sometimes we'll do things in joules, but a lot of this makes it easier if I'm working day to day with x-rays or I'm working day to day with those kinds of pieces of equipment. I don't want to have to be carrying around 10 to the minus 19 and making sure I'm getting in my calculator right. So that's why we do that. So equal potential surface, that's where, so if I'm drawing an equal potential surface and you're working in your lab, you can actually measure those. And we actually kind of looked at that a little bit. It's easy to measure those because I can measure. I can take a multimeter and I can actually measure where that equal potential surface is there. And if I'm on that equal potential surface, if I'm moving my electron around on that potential surface, no work is done. It's just like sitting on the merry-go-round. And if I go all the way around, I know where my start was. I know where my finish was. I didn't do any mechanical work. So that is something, those are some concepts that we work with on a routine basis. We can draw our equal potential lines. So they're going to be perpendicular to our field lines. So this is one way we can draw our electric fields. So here we have this there. And if I draw my equal potential surfaces as I'm going out from my charge, I'm going to get these like a topographical map. You know, here's the altitude that I'm at. I move further away, I'm at a different altitude. And we get those things that are perpendicular. So I can take my multimeter and actually measure my equal potential lines, and I can actually draw that, and then I can infer what the electric field is going to look like. So when we actually do this on a piece of paper that's a conductive piece of paper, we take a multimeter, we draw our equal potential lines, and then we draw in our electric field lines. So you kind of do it a little bit backwards. So here's our dipoles, and we actually showed this a little bit when we were explaining that laboratory. Halfway through the middle, I've got this nice line here, an equal potential line, and you can see that I've got these things building up, and we've got our equal potential lines, and we can infer what the electric field is going to look like. How do we use this stuff? Electrostatic precipitators. One of the big ways that we can do it. A lot of people have electrostatic precipitators in their house to collect dust and other allergens and all that kind of stuff out there. It helps us remove and purify air because we're going to use those equal potential lines, capture those charged particles, and allow us to move on. We use it for photocopiers. That's how we transfer the ink onto the paper, is through electrostatics, which is really kind of cool. So we use these concepts a lot in order to make things work. So like I said, we've got that. You can do it for sprayers, for 2-row applications. You can do a lot of different things for coating, spray particles, your printers, all of those items. We use these concepts of where the charges are in order to help us make devices. So our first device, even though you didn't know it, when you take 2 plates, you got a capacitor. and that's our first electrical device. We can actually store charge in our capacitor. And capacitance, we use them in electric circuits. You're very familiar with them. Probably not as much anymore. Used to when you went to a wedding and they gave you those disposable cameras with the little flash in it, and you turned it on and you got that whistle as the flash charged up. That flash is a capacitor. And when you touch the two plates together, it discharges all of those electrons, and that's what gave you your flash. Some cell phones have that little whistle up there. So your phone is filled with capacitors. Most of your flashlight functions, your flash for your camera, all of those are going to be controlled by a capacitor. Your keys on your keyboard of your computer. How does the computer know whether you're pressing a U or an M? You are discharging a capacitor, and that's creating an electrical signal to the computer that tells you which key was hit. And that's what's going to allow for that device. So we're going to define capacitance as the charge divided by the electrical potential. It's going to have a unit of a farad, and believe me, 1 farad is a big unit. It is a really big unit. We actually work in microfarads or picofarads, because you'll see those out there a lot, because this is 1 farad is a really large unit. My college physics professor, he brought in a 1 farad charged capacitor into the classroom. And he laid a wire across the top. And when he did that and the capacitor discharged, the wire went to oblivion. There was no more wire. The wire was gone. Poof, it was gone. We were all breathing the wire, because it is a very large item. So we deal with smaller things that are there. So the voltage actually represents the actual potential due to the charge, and we actually have that defined as a capacitance. So how do you build a capacitor? Pretty simple. You can take a plate, can be a piece of aluminum foil. It's got to be a conducting material. And we got another plate. If you connect a battery across it and you separate it by the distance, you now have a device. And we call them parallel plate capacitors. We can do a lot of different things that are there, but that is now a device. And you can actually take a multimeter, and if you know the voltage of your battery, and measure the capacitance across those plates. And this will actually, and so how we're going to define capacitance as a device, we are going to do that just now like this. We've got our permittivity of free space. Our capacitance is the area of our plate. D is the separation by the distance. And if I'm in air, I have what we call the dielectric constant is going to be equal to 1. If I'm not in air, like what's on your computer or what's in your devices, rubber, paper, wax paper, all of those things, those are measured devices, and we can put that in there, and we can actually build a device that has a specific capacitance. And we can use it and we can build it. It's pretty cool. Now, what's really cool about our parallel plate capacitor is that we can generate a really uniform electric field inside the parallel plate capacitor. It's non-uniform at the edges, and we call those edge effects. But remember, on the size scale of an electron, we can really get nice uniform electric fields. It's really great.
I have a question.
Yeah.
What's stopping those two plates from coming together?
Well, if I'm in air, these are physical plates that you just have them separated apart. Most of the time you'll have a substance between them, like a piece of wax paper.
Okay.
If I were to make one with aluminum foil, In fact, when I've done it inside a classroom as a demonstration, I put a piece of cardboard between them. And that gets back to I can't use K as 1. I have to use K for the cardboard. But if I could put a piece of wax paper, actually most capacitors, what you've got in your computer, it's usually a little rubber pad. If you've ever popped your computer key off, you'll see this little rubber pad that's there. That's between them. You'll see the ones, if you get a capacitor device, a lot of them have some sort of resin that's in there that's keeping the separation. So they're very easy to make. Now, what I did for my research project, my graduate research project, I looked at nanoparticles in a parallel plate capacitor, very much like the Millikan oil drop experiment. I had a positive and a negative, and I glued little strips onto a microscope slide. And so the gap was there because these were glued onto the microscope slide, but they weren't touching each other. I could connect a wire to this one, and I could connect a wire to that one, and I could create that uniform field for the thickness of my little strip of metal that I had. And when you're dealing with electron sizes and micro nanoparticles, you can get away with that. You know, millimeters a big thing when you're dealing with those little things. And millimeters are a really big thing. Think of Miss Frizzle, and we're all reduced down to nothing. So I've already talked about some of these items. Your battery attachment, the battery charges the capacitor, and the flash will come off. So that's one place that you see capacitors pretty easily. There's your key on your keyboard. That's another application. But we use them in circuits, and we're going to see that we use the capacitance to help keep our circuits as we're dealing with direct current circuits and with alternating current circuits. And so we use the capacitors to help keep our alternating circuits working the way we want them to. So we start drawing circuit diagrams. So this is a circuit diagram for our computer mouse. And this right here is going to represent our capacitor. This symbol right here, it has a little dielectric. And when I click my mouse, that's what we're doing. We're dealing with that click that's in here. These are resistors. You'll see that as a resistor. You'll see that as a resistor. These are grounds so that we can have our grounds coming in. And you can find electrical diagrams all over the place. And these are very helpful to do troubleshooting, look at things. These are diodes that we have as well. So we've got those in there. So when I have capacitors that are in parallel, so parallel is going to be, think of it as a ladder. So if I take a charge, now remember, Ben Franklin got it wrong. Actually, what really happens is my little electron is going to go this way, but we always follow the circuit from the positive to the negative. We got it backwards. But if I take a charge and I go here, the little electron is going to have the opportunity to go this way or that way. So think about it as a water. So if this is water, I can travel my water here, and I could either go down this branch or I can go down that branch. It has a choice. And then it comes back, and it has a choice when it comes back here. But these are considered to be in parallel. The flow has got to go this direction, or it's got to go that direction. Now, when I'm in parallel, when the capacitors are parallel, the flow of the charges ceases when when it equals the voltage of the battery. So they're going to positively charge These are going to be there. So the potential across this one, if I take my multimeter and I actually measure across this, and I actually measure across this, it's going to equal the potential of my battery. So if I start with a 9-volt battery, this is going to be 9 volts. That's going to be 9 volts. But my charges, I can count up all my individual little charges. So the total charge is going to be whatever charge is on this one plus whatever charge is on that one. And then we just add them up. So we can actually go through and add them up. So if I'm in parallel, my equivalent capacitance is just going to be the sum of the capacitors that are in parallel. And we will work through these problems tomorrow. But this is, you think about how the charge goes and you work through it, and we get our equivalent capacitance in parallel because we can play with that piece. So for equivalent capacitance for parallel, we're just going to add them up. Now, when I'm in series, things happen a little differently. My charge is going to come in and it's going to go to this one first until it's full. And then it's going to come over here and it's going to go to this one. So the magnitude of these charges are going to have to be the same, which is different than what we saw in parallel. So in series, I'm going to go through one and then I got to go through the next. Okay, I got to go through one and then I got to go through the next. And we start to accumulate the charge. And what's going to happen is I'm going to get an equivalent capacitance for that, except now it's based as the 1 over the individual ones. And these are going to get tricky. And what we're going to see when we get to resistors, it's going to be the opposite. Resistors are going to add up differently than capacitors. And I'll tell you that even today, and having done this for years and years and years, I still have to look up my capacitors and my resistors to make sure we're doing them right. Because it's easy to get them confused. And again, we're going to work through these tomorrow. So you've got those there. Now, the other thing is capacitors are an energy storage device. And we have 3 equations that we can use to determine the energy of a capacitor. And another place where we use capacitors and use that energy is a defibrillator. So your defibrillators are capacitors. And when we release the charge, we're releasing that energy through the heart. And that's why we're going to get that zap to try and jolt and get the heart to restart. So you have and this is going to come down to what these are simple equations, but you have to look at what the problem gives you. Problem will give you charge or capacitance. The problem will give you capacitance and voltage, or the problem will give you charge and voltage, but you can always calculate the energy stored in the capacitor. And that gives us our kind of overview of our capacitors. I'm going to go ahead and hit my exit. There we go. And that gives us our overview. And tomorrow we'll work on extra problems. We'll do some potential problems, and we'll do some equivalent capacitance problems. And then we'll look at charges on capacitors or voltages on capacitors. But you also have a lot of sample problems to I moved my camera, so it's hard to remember to look down instead of up. But I was tired of being this little space in a big blank. So that kind of gets you. So kind of questions that I can answer for folks.
I have a question on the electrostatics lab.
Okay.
Do we have to follow what